Hello, everyone. Good afternoon. I'd like to welcome you to today's Research Exchange talk. We have Dr. Mario Paniccia from Intel. He's a director of Photonics Technology Lab, and he's going to talk to us today about bridging photonics and computing. My name is Yvette Subramanian. I'm part of CITRIS, Publications and Events. And I have a couple announcements before we begin. As always, we have our Eye for Energy talks on Friday. This week we have a talk by Charlie Huizinga about demand response for lighting in commercial buildings. And this talk on Friday is not going to be webcast. So if you're interested in the talk and the topic, please be sure to come here on Friday at noon. And our Big Ideas student proposal competition is still continuing. We have $45,000 to award for student ideas, so you can go online and look up the rules. We had the workshops. The writing workshops are now online as well, so you can watch those videos and get an idea of what the competition is about. So as I said, today we have Dr. Mario Paniccia. He's from Intel, and he's the director of Photonics Technology Lab. He currently directs a research group focused in the area of silicon photonics, and they are developing silicon-based photonic building blocks for future use in enterprise and data center communications. So please join me in welcoming Dr. Paniccia.
Thank you. It's a pleasure to be here. I actually was saying earlier that I appreciate the nudge and the pestering to get me here, because it's always a pleasure to get back on campus. Sometimes you get caught in the real world, and it's actually good to come back. And I'm going to talk about what we've been working on in Intel, and put into context a new technology that we started this group, or I started this group, put in perspective, 2001. So it's almost a decade in technology and development of something that didn't exist. And I think it's very refreshing as I look out here. Part of why I like to get back on campus and talk to the students, and I think you guys are the next set of innovators. You guys are the next set of people driving new things, whether it's technology, whether it's business, and it's a great opportunity in your life now. As you go out in the world, don't be encumbered, right? A lot of people say no, and a lot of people say it can't be done. The stuff I'm going to talk about here, no one thought was possible, right? I had a few people at the company who gave me a chance, and you fight, and it's the advice in life: staying out in the cold, swing your bat, keep people away from long enough so you can prove them wrong. The irony is that same kid now, when I go in and talk to the CEO or the CTO, somehow my crazy ideas are looked at totally different, and I'm the same person. So, one advice as I start this, stick with your convictions in life, and don't let other people tell you. Don't let other people tell you. Is that better? It's not on? Oh, are you sure? All this? That was an awesome speech I just gave. How's that? Better? Did you hear what I said, most of it? Yeah. Okay. I don't think I can say that again. Okay, so let's talk. I'm going to talk about the motivation of why we started this. And then I want to put in the perspective of the evolution over the last 50 years of the electronic industry, the photonic industry. And then basically what we've done is combine the two. And then I'll go into our research program, and then describe the integrated link, what we announced last summer, and then show you the applications going forward and what it really means to you. There's a couple foils here towards the end that hopefully everything comes together, and what it means to have low-cost, high-bandwidth links. So if you see what's happening in the trends that happen today, if you go from left to right, these are different types of images or different types of technologies, whether it's retail customer, CT scans today, medical images, HD forecasts. As you move from left to right, there's the size of these files. CT scan today, is a petabyte of information, right? YouTube, right? That number keeps changing. We're talking 2 billion downloads or views a day at YouTube, right? This cloud computing, all this information is being stored on the cloud, enormous amount of information. The point is, where do you put it? How do you move it? And if you have all these devices connected together, moving it all wirelessly is very painful. So, one is, how do we move all this information? Another trend that's happening, and you see it in your home, TVs, flat panel displays are getting bigger, they're getting deeper in color, Movie theaters are competing with the TVs, so they're going to IMAX, they're going to 3D movies. You now have a 3D movie, it comes out on DVD, you need to put it into a Blu-ray player. And so there's a race that's happening to get the experience, bigger TVs, deeper color, price points keeps coming down. But what happens if you go all the way, let's look at full HD TV today, and look over to the right, at a 3D or at 120 hertz refresh rate, we're looking at bandwidth, just raw bandwidth to refresh the TV screen. It's about 10 gigabits per second. All right, to put into context, your USB connector today is 200 megabits. Okay? You scale that, and I was just in Japan about 6 months ago. This is the new standard that's being talked about. Quad HD, twice the resolution. Take that same thing and you scale it out at 120 hertz refresh rate. You're talking 25 to 50 gigabits per second needed just to refresh your monitor. You can do that. It's going to be a big fat cable, right? So it's going to be very difficult. And if you go closer to home, or closer to our home, or mothership, whatever you want to call it, and our server backplanes, this is a plot that I've shown for probably 5 years, the same plot. Data rate on the y-axis versus attenuation. And what you see is Moore's law keeps going. We keep pushing electrical, 10 gig, 12 gig. We'll eventually keep squeezing out a little bit more. But we're running into fundamental limitations of how far and how fast we can push signals over electrical. And so all this screams for, can we come up with a better way? Can we use optical and the benefits of optical to do something different? And we look at it two ways. One is, if we look at the consumer side, everyone has a handheld today, tablets. Just think we have all this information, but you have a tiny screen. If I have all this information, I want to show it on a monitor or show it on a TV. The ability to have a small fiber, plug it in and now show it on a large resolution. The ability to have your information and store it somewhere and just grab it when you need it. But not just grab it slowly, grab it quickly at very high speeds. The ability to repartition the platform and thinness, lightness, architecture. Who's familiar with Thunderbolt? Everyone's Thunderbolt? Apple fans? So that was a technology I started in my lab 2006. And to put it into context, it used to be called Light Peak, and I'm going to go into the discussion here. And then, Steve actually personally picked that technology, and we decided to go to copper in 2010. The whole point of that technology was about thinness. Remember, in 2006, 2007, MacBook Air didn't exist. The whole point of that concept was high bandwidth, low cost, so we can get rid of the VGA connector. So the ability to have this technology on the client is about architecture, thinness, lightness. In the data center, we're seeing massive amounts of traffic. And the ability to stretch things out, to separate things. 50% of the cost of a data center today is in cooling. But electrical means we have to put everything close together. If I can just separate things and cool them differently, the ability to separate I/O server, the I/Os from the server, from the memory, this ability to have this technology would allow us to completely revolutionize the way we design systems, the way we architect systems, and the overall performance of these systems going forward. So it all sounds great, and you say, well, what's the problem? Well, the problem is, at the end of the day, it's about cost. So this is a plot showing decreasing distance from left to right. This is the telecom, long haul. Anything over 10 gigabits per second today, probably over a kilometer, is all fiber. Right? Obviously, long haul telecommunications. As we move to the rack to rack, shorter distances, you're starting to see this transition from copper to fiber. And all the way to the right, you see chip to chip or board to board, it's all copper. On the y-axis, you see volume. And you see there are billions. So if you just look at copper traces, it's billions, if not hundreds of billions of interconnects per year. Here, we still talk in terms of hundreds of thousands to millions of modules. More importantly, on the left, we still talk about in terms of hundreds of dollars per connection. And the upper right, we talk in terms of pennies per pin. So if we want to bring the benefits of optical there to the right, in and around the PC, in and around the platform, it's about driving. You can't take a gold-plated box, shave the gold off, and expect it to be cheap. So we started saying, we said, hey, can we do it differently? Can we take the benefits of what we've done with integration, IC, Moore's law, right? This is the first transistor, 1959. And if you scale today, it was 50th anniversary 2009, we've gone from 2 transistors to today we integrate billions of transistors on a chip. What's really happened with that, with the integration and volume manufacturing in silicon, is the ability to get more, faster, cheaper, smaller. Right? And what you have today in a handheld or a phone is what you had in a mainframe 10 years ago. So this is what silicon integration and Moore's law has driven to the industry. Ironically, last year was the 50th anniversary of the laser. And you know, when this was the first laser in 1960, it was a big, bulky. No one really understood what the use it was for, but we understood how it physically worked. And if you fast forward today, lasers are used everywhere, from simple laser pointers now that you can just buy, to medical, to surgery, to welding. And it is the technology for telecommunications. And the reason it's the technology for communications is because photons, which are the key particles for light, don't have mass, and they don't have charge, and so they don't interact. And so I can send signals very far if I can confine them in a fiber, whereas in copper, you have discontinuities in the copper, you have electrons that have charge, they interact, and so you basically can't send electrical signals as far and as fast. So we said, what if we could combine these two? What if I could take the benefits of silicon manufacturing, the benefits of high bandwidth, high-speed interconnects, and combine those so now I have a massively high-volume, low-cost produced solution that I can put optics anywhere. And think of it as the analogy of wireless today. No one talks about putting or going to a store and paying $100 for an add-in card anymore to put a wireless. I don't know if you guys remember, it wasn't that long ago, 7, 8 years ago, if you wanted wireless, you would pay $100, you put the card in. Today you get it because of integration, you get Wi-Fi, 3G, and even WiMAX. And it's a given that you have wireless. So we'd like to look at it going forward, maybe in the next 3 to 5 years, we start thinking of optical as a technology that just becomes part of the platform, part of the embedded devices, and then we start thinking about what do we do with the technology instead of how do we afford to put it in. So that leads to, well, how do we do this? How do we go about doing integrated silicon photonics? And so the first thing you do is how do we build an optical link? And so, you know, I put this flow set together. So you start off with a laser. You then need some way to encode that data. So I have an optical beam. I then chop it with some kind of modulator that puts the 1s and 0s onto the beam. We then put it through a fiber where we connectorize it, send it down a fiber, and then we bring it to another side, which let's call it a photodetector. Think of this as a solar cell that converts the photons back to electrons. And from that, you have an optical link. We also have the ability of photons, because they don't interact, you also have this thing what's called CWDM or DWDM, wavelength division multiplexing. And what that means is I can take different color lasers or different wavelengths technically at a different spectrum, and I can combine them down a fiber, and because they don't interact, I can get very high bandwidth density down a single fiber. So the ability to have multiple lasers or multiple colors down the same fiber means for one fiber, I can have enormous bandwidth density. Whereas in copper, I have to have, for every signal, a different trace. So again, you combine all these, and I said this earlier, the big problem is cost. Today, optical technologies are on what we call exotic materials. Right? So anything that's not silicon, to us it's exotic. Right? And maybe it's... And so indium phosphide, lithium niobate, gallium arsenide, these are non-group 4 materials that are expensive. Indium phosphide, which is the predominant material for optics, is still on 3-inch wafers. Today we're shipping 300 millimeter, 12-inch wafers, and we're moving to 450 millimeter wafers. Right? Just to put it into context, so you know, indium phosphide, although it's the optimal material for photonics, it's 10 years old technology. You can't expect to bring that technology into mass market and expect the cost differences. So we started on this program. We said, hey, if I want to siliconize photonics, you essentially need to do 6 things. You need to first build the building blocks. We need to build the transistors and prove that we can build optical devices out of silicon. So we need a light source. We need a way to guide and route the light. We need modulators, right, the way to encode the data. You need a way to detect the light. you need to then, even if I could build all these first 4 out of silicon, if you don't assemble them in a low-cost, high-volume manufacturable way, packaging, testing, and assembly is probably 50% of the cost. So if I take a Ferrari and I assemble it, but I don't figure out how to put that Ferrari engine into, I don't know what, a different low-end car, Ford Focus, you don't have a cheap car, right? And then lastly is the intelligence, and that's CMOS. The bits always start off as bits, and we transmit them, but we have to convert them. And so over the last decade, and this is what my team has probably been focused on, each of these milestones are the building blocks that we've developed. And those dates are the dates of publications. And the irony of this is each of those publications are Nature or Nature Photonic papers. So they're big steps. And to put it into context, and the reason for this is silicon inherently, prior to this 2004, was not a good optical material. It doesn't laze. So if you want to get light to emit out of silicon, you look real close, it'll glow, it'll melt, and then you see a little puff of smoke. That's the way silicon lasers. It doesn't work. It doesn't have an electro-optical effect, so you can't rotate the light. So it doesn't have the optical properties, and that's why no one's used it. But if I just focus here on the silicon modulator, prior to this publication, the fastest modulation in silicon was 20 megahertz. I came back, I made a bet with my team that I just bet the CTO that we were going to hit a gigahertz by the end of the year. This was January 6th, right after the holidays. I nearly had mutiny on my staff because how could you do that? I said, well, it's even worse. It's not only a bet, but we agreed that he would take it as his corporate deliverable. So it impacts his bonus. So we're going to hit a gigahertz by the end of the year. And everyone said, you can't do that. How can you do that? What, 500 megahertz? I said, look, it's gigahertz. The bet's already made. Let's go do it. That same team, when we published that paper, we hit 2.5 gigahertz. A year later, we pushed it to 10 gig. And by the way, the gigahertz and gigabits is written because that was the title in the technical paper. And then a year later, about a year and a half later, we pushed it to 40 gigabits per second. So this is something no one thought we could do. My team didn't even think they can get there. And today, we're not arguing about 40. We're arguing about how to get to a terabit. So there's a psychological piece here, and this is part of what I want to instill in this audience here, that don't be encumbered by what hasn't been done. Right? There's a psychological thing here that happens. The physics hadn't changed. It's still electrons and holes moving into silicon, but it's using that in a different way. 40 gigabit per second photodetectors, the first Raman laser, lasing in silicon, a hybrid silicon laser, which was done with the University of Santa Barbara, and the fastest avalanche photodetector ever reported. These are milestones that have been achieved, and now we've proven we could build these devices. We now have the transistors. And this is about being good enough. We're not trying to solve a 100-kilometer problem. I'm trying to solve the 5-10-meter problem. And so we have these building blocks. And if you remember what I said, the benefit of integration and ICs, it's not 2 transistors. It's what happens when I put these things together. So if I overlay this thing on a link, I now have a laser. I now have a modulator. We've developed passive waveguides, how to split the light, how to couple the light. And then we put the detectors together, and lastly, we also focus on the connectors. So now I have all the pieces to build an optical link, all devices made out of silicon. And that leads to the 50 gig link. So fast forward a few more years, make the same trip to Portland, different CTO. We get in a little debate about, you guys, when are you going to put all this stuff together? I make a bet that we integrate this by the end of the year. It changes to even a higher level where he now decides to make it a corporate deliverable. So he get 2 that take up, so now it affects all employees. Can you imagine I fly back down to Portland? Our CTOs work out of Portland, I don't know why. And now I come back to my team and I say, hey, I just made a bet. We're going to integrate. I made a deal that we would hit 40 gigabits per second by the end of the year. This is now December, so at least they had an extra month. It wasn't just 12. Same argument, same thing. I said, here's what we're going to do. Not only are we going to integrate the photonics together, but we're going to do it with low-cost packaging. There's no thermoelectric coolers. It's going to be PC-like manufacturing. We're going to assemble it in the PC line, and we're going to have this running just like it would in a PC. Gave a few ARs to the team. Let's get back together in 3 days, and let's kind of dissect the problem up and give ownership. And I tell this story for a reason, right? So we come back, and I sit around, and by the way, I didn't know how to do it all, but I figured enough that we could put it all together. The time constraint is an added, as a manager, it's a plus. From a stress level, it's a minus when you have those kind of aggressive goals. And I sit around the room, and everyone's saying, I did a literature search. No one's done this kind of packaging before. I did a literature search, and no one's ever published doing this kind of stuff. No one put all this, no one's put a hybrid laser together with a modulator. And I sat back, and I said, look around, guys and gals. I have females on my team, too. I'm always sensitive to politically incorrect. My apologies. And I said, look around the room. Who did the first modulator? Who did the 30 gig modulator? Who did the 40 gig modulator? Ling, you did it. Who did the first hybrid laser? You did it. Where was those publications? They didn't exist. Those publications are now yours. So we're at the Super Bowl again, right? We're going to go do it. And, there's a piece here. It was a surprise to me. That human nature is the fear of failure. Here's the team that did all those world records that everyone else uses as the benchmark. And we were going to go play again and do the next one. And they didn't think they could do it. They didn't know how to do it. But what I'm going to show you is we did it. And we did it, and we far surpassed what we were going to do. And I want this piece to all of you as you go out. And, you're still young, for lack of better words, and you have the professors here. Don't be encumbered. No, really. You guys, that story, I don't know how to resonate because I went home that night and I didn't know what to do because I'm like, if this team can't think it can do it, who's going to do it? And I had the pleasure to work with Apple and, with Steve in his reports over the last 3 years. That mindset over there is totally different. That bar is so high, they do things that they don't know how they're going to do it, but they never lose sight. And I want, if anything comes out of this, and I'm going to tell you what we're going to go here, walk out of here with that mindset, right? There's everything you're going to go touch in life hasn't been developed yet. You guys are going to go do that, or have an opportunity to go do that, right? And so here we fast forward, and I'm going to actually show you. I'm going to pass these parts around, or this one part. I need it back because I have a lot of them. But this is the 50 gig link, right? So this is the world's first, where you have a transmitter. This is the transmitter. The long piece of silicon is the transmitter. This is what's in there. I'm going to walk through it. This is the receiver. So what this actually does, we have two pieces of silicon put on PCB board that communicate between them optically. They get fired up, nothing else, and the whole thing is processed, and now we're communicating between two chips. So the first thing is, as I said, silicon doesn't laze, so we've taken this approach, think of it as a hybrid car or hybrid electric car. We call it the hybrid silicon laser, where we put a little bit of indium phosphide down. That's the orange. And we bond it to silicon. And what that allows me to do is take a little bit of very expensive material and only use it where I need it. And then I use the silicon for the lasing material. And we're able to do this with one bond that can create 10, hundreds, if not thousands of lasers. More importantly, the laser is determined by the silicon. And what we do, there's the indium phosphide, the orange. It's not really orange, by the way, it's just a cartoon. This is what it looks like. There's a picture of the device with the contacts. The light, indium phosphide emits light. You apply a voltage to it, it emits light, and now the light gets sucked down into the silicon, which is the gray piece here. And it bounces back and forth. And we have gratings that are etched in the silicon, and those gratings will reflect a specific wavelength depending on the etch depth and the periodicity. It's called a Bragg grating. And so I can create whatever wavelength I want, and the light will bounce back and forth. Eventually, the amplification exceeds the loss, and I'll get a laser. I keep pumping it, and eventually I get light to come out at the specific wavelength of interest. So you see a very precise, only that wavelength gets amplified, all the other ones get diminished out, and that's the concept of light amplification by stimulated emission, which is a laser. And you see we get very precise, very accurate lasers. The benefit of that is this. This is a cartoon. This is the actual transmitter chip. The chip that's being passed around, it's packaged upside down. These are the contacts. So we're looking at the die, the laser sections on the left, and the modulator sections. I have a laser pointer for a laser guy, right? I should probably use it. So this is the laser section. This is the modulator section. So inside here, because of that hybrid laser, I can etch gratings, and I get, and this test chip was 4 different colors, or 4 different wavelengths. They then go through a modulator array. This is all one piece of silicon. Where the way the modulator works, it's a shutter. So I bring in a bunch of electrical ones and zeros, and the modulator will encode that data. So the lasers fire up. They run continuous wave, just like a flashlight, always on. We encode the data. It then goes through a multiplexer, which combines all those channels and then gets output a single fiber. So that's 50 gigabits per second coming out of that chip that's being passed around. And by the way, if anybody was paying attention, what did I say the bet was with my CTO? Anybody catch that? It was 40, 4 by 10. So if you notice, when we went public, it's now 50, which I always tell my team they sandbag everything. And it was we pushed it a little harder. We were actually able to push it to about 12.5 gig. On the receiver side, you take the light in. You now split those 4 colors back up in this piece of silicon here, where we split those channels back up. See, this is the benefit of doing things with optics, is I can run multiple colors on the same fiber. I split it up, and then it goes into a germanium photodetector, which converts the photons back to electrons. And so 4 by 12.5 gig, I get 50 gig transmitted from one chip to the other. The other thing was the packaging, and this was a lot of the effort. So this is that transmitter chip which is being passed around. This is the driver IC. So this is an IC. It takes in small signals, a couple hundred millivolts. It amplifies those, and then it's impedance matched to drive the driver. In the future, this will be a CPU. This will be a chipset. This will be FPGA, whatever you want to use as your drive source. We also then put these little tiny pins for this first generation. If you notice on these parts, there's always these lines here. These were these pins we used for alignment, where we actually then made this is a plastic molded connector. It's probably $1 in high volume. It's sent out, it's molded, and there's little holes here that get into these pins. The fiber comes in, and there's a lens here that gets coupled in to the silicon chip. It's not, you would never use this for telecom, but it's good enough for the applications we're using where I can afford to lose a couple dB. But the key thing is all this was assembled in the same process that we do all our packaging. So not only developed integrated silicon photonics, we package it and assembled in high volume. This is the test bed where these are all the control electronics. This is the transmitter that sits here. This is the receiver. And in the lab, we actually ran it over about 5 meters. This is some of the results. I think it's only one technical foil here. So this is the 4 wavelengths, 1290, 1310, 1330, 1350. So we have 4 lasers operating at the wavelengths we chose. This is the multiplexer. This shows the envelope of how well the multiplexer works, which is aligned with the 4 laser channels. And then this is the data stream of the transmitter being plugged into an oscilloscope, looking at a pseudo-random bit sequence of how good the data transmission works. This is the receiver side showing you how well the light gets split up into those 4 channels, 1290, 1310, 1330, 1350. So into the receiver chip, I first split the light up at the exact same wavelengths, and now I can convert the photons back to electrons. And the thing here that came out of this is the target, with everything, you always have goals and targets. The target for a product, the optical link, is 10 to the minus 12 bit error rate. Does anybody know what bit error rate means? So when you look at link performance or systems, it's how many bits can you send before you have an error. And so when you're doing some stuff with compression on the internet or Ethernet, you always have packets, you refresh them. When you're doing high-performance computing or banking, you can't afford that. So the spec for high-performance computing or bankings are 10 to the minus 15. A typical optical link is 10 to the minus 12. We ran this system, again, it's not a product, for 24 hours in one experiment. We transferred about a petabit of data. This thing was sitting in the lab, and we were getting bit error rates of less than 3 e to the minus 15. So with 95% confidence, that thing ran without a single error over 24 hours. And we sat back and said, wow, we made that's a big, even I was surprised. And it basically said, it just gave you a concept because, and by the way, part of this is we pushed to do all these other things. But the takeaway between doing this challenge, getting it to work, and the bit error rate said, oh, wow, we can take this to commercialization much faster than we thought we would have, or if we just took half the step. So that leads to what can you do with this, and why is 50 gig so important? And that leads to the next couple foils, which sort of says, hopefully if I can kind of put the fact of all this together, what does it mean to you or to the consumer and to the future? The first one is this. We'll call scale up and scale out, or what we call scale up and scale out. So 4 by 12 and a half is no magic number. 4 is not magic, and 12 and a half isn't any magic number. If you remember when earlier with all the records, we have most of the devices in the lab running at 40 gigabits per second. So if I take that 4-channel device and I just optimize the design so the modulators run at 25 gig, I now get 4 by 25, and that's 100 gig. 4 is no magic number. We just said, let's do 4 as 2 is too small, 8 or 16 is a lot of work because it's a yield reliability thing when you integrate lots of devices. But if I take that same 8 by 12 and a half, I get 100 gig. And now if I take any multiple, if I do scale up and scale out, and let's just say I do 25 lasers at 40 gig, that's a terabit per second. So we're talking about a terabit per second communication coming off a chip the size of your fingernail by integrating these devices together. The world record today is 26.4 terabits per second. I think Alcatel-Lucent still has that. It's a 100-kilometer link demonstration, but the equipment to do that fits a room about the size of this room. So we're talking about now putting all that down into a chip. More importantly, if I look at this, or when you look at this, 50, 100, 400, what do those numbers mean? If I look at the consumer space, Thunderbolt is at 10 gig. Future generations or derivatives will go 25, 50, 100 gig. I now have a technology that I can apply to the consumer. I integrate more devices, and now I can do 100 or 400 gig. 100 gig is an entry point into the data center. 200, 300 gig allows us to look at CPU to memory. And then at the high end, high-performance computing will take all the bandwidth you can get. So we have a common technology that by integrating more or less, I can take a broad, across multiple applications when I start looking at where I can apply this optics. So, sounds really exciting. Went home, was talking to my wife, and had to tell her that we were going to cancel our vacation because our CTO wanted to make an announcement, and I already planned our vacation. And so I said, well, we did 50 gig. You don't understand, honey. And she said, I don't understand. And so I said, just think about it. 50 gig, you can transfer an HD movie in like a second. And her reaction was, oh, wow, that's really exciting, right? And I was and so I went back and I had one of our marketing guys do this analysis. And I think this puts it together, right? At 50 gigabits per second, and this is not 10 years from now. This is stuff we have today running in the lab that we're looking to commercialize. You can transfer, when you do the number, that calculation actually came out, you can do transfer an HD movie in about a second. You can do 1,000 high-res photos in about a second. And if you're a big tweeter, you can do a lot of tweets. All right. More importantly, what happens at a terabit per second? And this is, again, the ability to integrate and scale will happen. It's just good engineering. At a terabit per second, we're now talking about 2 or 3 seasons of HD TV shows that you can transfer in a second. We're talking about backing up your hard drive in less than a second. This is a calculation for a 160 gig hard drive. And, you know, if you look at the other end, calculation at a terabit, you're talking about the entire printed collection of Library of Congress in about a minute and a half, right? So this is the kind of capability and bandwidth that we're talking about enabling once you can get this into a platform, into a silicon platform that you can bring in and around the PC and servers. And it takes time because you have to enable the ecosystem, you have to put it, but this is what we're talking about doing, and as we start moving more information and having more information, the ability to bring this in and around the platform and in peripheries is what we're actually trying to drive in the next few years. So I have a cartoon. What does that look like from a chip level? You know, we're looking at Moore's law doesn't stop, so we keep integrating more and more cores. You start looking at stacking memory. At shorter distances, remember that first of all, optics doesn't replace everything, and wireless exists. So it's going to be optical, wireless, and then over short distances, copper traces will still work. So this is a server, but more importantly, now we're talking about putting high bandwidth optical chips at the end of that server, which now can communicate from one board to another board, from one room to another room. You can imagine I take this terabit chip, I start putting it down onto boards, put it on the PCB board, and now I can start putting these on every server every PC, every platform, and now I have an entirely different way of how I connect things, how I design systems, how I repartition the platform in the data center. And I think this is, and maybe I'm biased about revolutionizing the way we can push information and use information in the future. So I have two photos on challenges, just so it's not all. One thing, and this is more maybe for an engineering, electrical audience. Everyone says, well, geez, if we're going to do optical, why do we do electrical? Well, you have to understand that the bits are all electrical. And the phis and the electricals that drive it are going to be electrical. So one is, you're always going to add optics to something. So if you want the lowest performance, best performance system, you're going to have to add some power. And power is a big focus today in the data center and to systems and battery life for handhelds. So I said there's no free lunch. So we're going to selectively decide where and when and how to put optics into the platform. It doesn't go everywhere. But we're going to apply it where it adds value. In some cases, it's about bandwidth. In some cases, like the Apple with Thunderbolt, was about industrial design. In the data center, it's going to be about cooling and reach and separation. Secondly is what I call more the practicality of it. You see a test chip that's being passed around in a lab prototype, but eventually you got to put this into a system. You got to put it next to a CPU, and our servers are 150 watts. How do you put an optics module next to a 150 watt CPU? Right? How do you take advantage of that? How do I package it? How do I test it? Do I start testing our CPUs first electrically, and then do I test them optically? What happens when, on the consumer side, if someone sticks sticks their connector that has an optical fiber into peanut butter, or licks it, or puts santan lotion on it? I mean, things that you never would have thought of that we're now going through. How do we make this consumer-friendly technology so that people can use it? Because it's a paradigm shift of what's been done in the past. And so a lot of these things are, these are the key to enabling this technology in the next few years. So lastly, I'll summarize, and hopefully have time for questions, is that, hopefully I gave you a big picture of what we're trying to do and why, and the concept of what silicon photonics is, the ability and the correlation of silicon photonics essentially to the integrated circuit. You can think about those big vacuum tubes to the planar transistor. We've now taken these big bulky devices, the ability to put those in silicon, and it's just the start of driving this technology, right? Bandwidth capabilities from 50 gig to plus a terabit by integration. And more importantly, it's the ability to drive new form factors, new architectures, not only in data-intensive applications, but I think silicon photonics will have a much bigger impact in other areas. We're focused on communications right now. That's our focus. But if I want to build a biochip, it's the same things. I need a laser. I need lots of lasers, lots of detectors. I need some kind of spectroscopy. And instead of sending light down a channel, I want to put microfluidics. So you have all the components for a biochip in principle. You have all the components to do wireless sensors, to start gas sensing and air sensing and do more complicated things. And in order to take this out to the mass market, it's now about, we need to enable this entirely new industry. How do we test this stuff? How do we build the wafer level testers? How do we build, because this is not about shipping 1 million of these, right? With one OEM, overnight we'll ship 50, 100 million units. And so it's this daunting task of bringing up this new ecosystem to enable such a technology, but it'll happen very fast. And I hope, this group in the future will be the next generation that figures out what can we do with this. If you had 100 gig capability and it was there, what would you do differently? How did you use this information? How do you use this technology? And part of what I heard for CITRIS is to benefit humankind and society, I believe was what he said. So thank you very much, and be happy to answer some questions.
I have two quick questions. One is, since glass is silicon, is there a way to convert it? And that's what they use for fiber optics, right? Or some derivative thereof. Would there be a way to use silicon and turn parts of the silicon into glass that you could do the high bandwidth transmissions?
So, silicon is essentially sand,
yeah.
And glass is some derivative of sand, I believe, right? But you have to understand, fiber's cheap.
Yeah.
It's like 3 cents a meter.
No, but I was thinking that you could all integrate it on one chip. You have, it's just an idea that came on when you said, we can't send high data through silicon, and then you showed you could.
Yeah, so the point is, what we actually do, when you look at these things, we're actually sculpting waveguides. The way the light routes in silicon is we actually create passages for the fiber, for the light to route. But getting it from point A to point B, you still have to put it into something, some conduit. Okay. And that's where the fiber is used. The fiber's not used on chip, it's just connecting between things.
Okay. Yeah, no, what I was thinking when you were saying moving things on the chip, to do kind of, I guess, what you did. I didn't really go into detail on the process on how you did it, but I was just saying, in silicon, it's glass, fiber optics on the chip. The other quick question I have is, what did you do with Apple? Did you work for Apple, or did you?
No. So, a lot of this, now it's publicly out, but, the way these work is, so, Intel and Apple and other OEMs, we always do, I don't call them secret projects because Apple's a real secret projects. We started talking about optics, and at that time, to put in history, we didn't think we can get 5 gig out of USB in 2006, so we had discussions, we had a couple of meetings, and over dinner, we said, hey, if we can do 10 gig, we can get rid of the VGA connector. We signed a little napkin. I got in trouble for that, where we both signed it, and that turned out to be the contract. And we started working at 10 gig optical. 2 days later, I went up to Jobs, and he sent a note to Paul, our CEO, and said, this is the greatest idea I've heard. And so we ended up together working on this project to enable and launch. At that time was LightPeak, until we named it. And so for 3 years, my team and that team, we developed this technology together. And it was, so that's what I meant by working with Apple, right?
No, I think that's a great idea. I showed Andy Grove how to use the Next machine because he'd never used one, and he tried to convince, before the Apple adapted it, that they should be running on Intel processors. So I'm glad to hear you guys are working together.
And so it was a very great learning experience working with Apple. I mean, we should talk afterwards. But the point is, I just want to say this is something that it took 4 years. I mean, these things start really early. 4 years to launch that technology with 2 of our companies together driving it, right? More questions? Yeah.
Hi. Very nice talk. I have a question about the indium phosphide laser source.
Sorry, go ahead.
How reliable is it to stamp a bunch of these indium phosphide sources on silicon? Is that sort of what you think is going to be the continuing solution for the upcoming generations, or do you think you're going to transition into something that's more integrated?
I mean, I think how reliable is it? Ask me in the next year or 2 when we commercialize it. But that's, getting the technology through the reliability gates, I call it the valley of death, right? We're taking these devices now. What you see there that I passed around, I need that part back, by the way. I would like it back, anyways. Is that these are not optimized for power, for size, right? So the next generation that we've already been working on is an optimized small form factor, commercial form factor. And we're now taking it through the chicken tests. Everyone heard that, what chicken tests are? So we hired some senior reliability guys to come in and he started talking chicken tests. And I looked at him and I said, what does that mean? He says, well, and this is what the reliability guys still use. So in the old days, when they started putting in jet engines for planes, the way they would test them is they'd throw chickens through the engines. That's the worst case scenario, right? And so they still use that. So we're going through the chicken test now where we take these things, we put them in ovens at very high temperature, we shake them, and we're breaking out the reliability of these devices. And we have to go through those at accelerated tests to try to map out the lifetime and commercialize. So, the laser's a huge opportunity for us, but it's also the biggest risk because it's new technology. And there's a lot of trade secrets of how we're actually doing it, how we're processing and manufacturing it, but...
And can it scale up with production? As far as, if you want to have, I don't know how many you want to ship out per year. I mean, can you stamp them out quick enough?
I think we have plenty of capacity, so we're always looking for more business. Yeah, that's not a problem.
Thank you again for the talk. It's great. I was just wondering, aside from transceivers, are you guys building other optical components, like, for example, like optical switches or anything like that?
When you look at the stack up, right, the first thing is to try to drive, optical links between systems and servers. And so whether it's in the data center where we're looking within racks, rack to rack, in the consumer space, PC to periphery, once you have that, the next logical thing is starting to address the next layer, switching and routing. And I think it'll evolve. Right now, my group's not focused on it right now because There's no value of developing silicon-based optical switches if there's no optical links between things. But that'll be the natural evolution. So I think it'll just keep moving up, and everything that Cisco and Juniper are doing today will eventually end up being part of a system in 10 years, right? You're going to have your house, you're going to be routing different colors. I mean, I think it's just that evolution. Any other questions? Question back there.
Oh. So you mentioned moving optical communications to chip to chip or within the chip. But that indium phosphide laser you showed would take up a lot of sort of horizontal real estate for like if you're actually building it on your CPUs or something. Do you have an idea of like what a different light source would look like if you're sort of building it onto your CPU, or real estate's really expensive there?
So I don't think I said that, but what
sorry.
I did say, no. What I mean by that is I think on-chip communication is a long time off. I mean, I'll probably be retired before that. I mean, two things. 10 years from now, 10 years in this business, in this industry, is eternity, right? Things change so fast. When you look at the next 3 to 5 years where you have a line of sight that's predictable, the reality of where you're going to put optical is solving the 2-meter problem and the 5-meter problem, and then you go down to 1 meter. And within a system, within a chassis of 12 inches, I think copper will be fine for a long time. So we're a long ways away from justifying the cost, the real estate, all the things you said, of trying to do within chip, communication, because it's cheaper just to die stack more layers of silicon than to put a photonic piece, right? So everything I show of all the cartoons and even the pieces, you see an IC and you see a silicon photonics next to it. So whether that's a CPU in the future, we're still going to co-package for a long time. We're a long ways away from marrying those two processes because it's too expensive, right? So that makes sense? It'll happen, but it's all driven by costs, and the costs tell you keep them separate as long as possible. I mean, there may be some high-end military applications that justify that, but not in the volume mass market for some time. And hopefully that's not your thesis project or something you're working on. I don't mean to diminish you, but those are the kind of stuff that you guys should be working on.
Okay, well, thank you again for a fantastic talk.
Thank you.